thank you. Thank you very much for the invitation to the opening of this exciting new group in combinatorics and probability. In my talk, it will be a bit atypical for this little workshop because I will not speak about probability at all. I'm gonna, on the other hand, talk about a very nice tool of extremal combinatorics, which is helpful in a problem of combinatorial optimization. So I will focus on this one problem, which you can read in the boring part of my title, which is just that improved integrality gap for restricted max-min allocation. And now I explain the main title, or at least one part of the main title. So I will talk about the Santa Claus problem. I prepared a little drawing. You can see my talent, right? So this, oh, no, this was not good. Okay. Okay, so this is Santa Claus, and right. And he has these presents, which he needs to distribute among these three children, which you can see. And the presents have some value, which is like a catalog value. So there are some cheap ones and some medium ones and some more expensive ones. And each child has set up some preferences, right? So that which of these items they would like to receive. Oh no, this is not a good color. Maybe let's choose another one. Which item do they want to choose? Which item do they want to receive from the Santa? And they name, say, the iPod. And an iPhone, and also some cheaper ones, but maybe they also want the same item as the other children. Okay, so this is done for each child. Okay, and yeah, some items are liked by several of them. And now Santa has to distribute them. And this means these items are indivisible. So maybe he will create this set of liked items to this child, and then this to this child, and this to this child, and now somehow has to measure how satisfied these children are, and what we choose as a measurement is that we add up this monetary value, and we assume that the children are more happy if they get more expensive gifts. And then this child is, how happy is this child? It's the 10, right? So it's a 15 happy. This is just 7, and this is just 7. So this is not really good for this green and blue child. So maybe he can rearrange somehow, namely would take this green to the green, and maybe would take this 4 to here, because these are liked by those kids, and this way we get a more favorable, more equal distribution. Namely, here we have 12, and here we have 6, and here we have 11. Yeah, I'm not sure whether this is the optimal one, but this you get the picture that we would like to distribute the items to help Santa. I did not come up with this fairy tale for this problem. It is how it is known. So Santa's goal is to make the saddest child as happy as possible. Okay, so this is now the saddest child. So let me say this formally. So in general, we will have in a problem instance a set of players. These are the kids. We will have a set of resources. These are indivisible resources. These are the toys, the children, the gifts the children would like to get. And each has a catalog value, which is positive for each resource. And each child identified a subset of the resources which they want to get. Maybe they already, I don't know, have the probabilistic method book. And this is our basic setup. This is the problem instance, and we are looking for an allocation. So an allocation of the items to the players. So for each player, we identify a subset of its liked set, such that these sets are disjoint. Okay, and what we measure is the mean value of this allocation, which is just the minimum of the sum of the values each child receives. Okay, and our objective, of course, is to maximize this minimum over all allocations, and this is what we call this optimum. Yeah, so one could argue to some extent that this is a reasonable parameter of overall individual fairness. If these resources are desirable, there is a sort of dual of this problem when we can imagine the resources more like chores, jobs, when we would rather want to minimize the maximum. And this is the typical example when we schedule jobs on machines and the classic makespan minimization problem. Okay. Please stop me whenever there is any question. So a little bit, obviously, we are interested in learning about these problems, potentially finding algorithms to aid calculating or dividing these resources and determining the complexity of the problem. There were some works already earlier in very special cases by Wöginger and Epstein and Schall. Now, what for us is the most important result to start with is this derivation of Bezakova and Dani, that better than 2 approximation solution is unlikely to be found. So we have to look for approximation algorithms to approach this task. And immediately when we write down the sort of obvious linear program and hope to make a integer solution by rounding or something, we face that the obvious one where we assign variables to each pair, player, and resource, and we set constraints for each resource that we should not take more than one, and we should measure that each player gets at least a value which is some given t, and we maximize this t. So this is a linear program which will have an unbounded integrality gap trivially, if we just have one very valuable toy that every kid wants, and the number of kids is at least 2, then we can obviously give this toy to only one kid. So the optimum integrally will be 0, but fractionally we can divide equally between the kids. So this is, this is not good. And Bansal and Sviridenko, this is it is in their paper where this problem name was introduced, suggested a more complicated but more effective LP, the configuration LP for the problem, in order to deal with such instances. So I would like to explain this LP a little bit in some detail, because the whole idea how we apply our tools for independent transversals is dealing with this LP. So that requires a little bit of sort of attention. So suppose that we are given an instance and we identify a target value t, which we would like to achieve, yeah. And then we, with the help of this target value, we will identify a set of subsets of the like set of each child. Okay, so these C's we will call configurations if their value is at least t. So this means that if our target is t, and this child will get this set C of presents, then this child is happy, satisfied. Okay, so an example in this drawing you can see. So here is the Santa's backpack or sack, and this child likes this set, this blue set of items, and among them the values are distributed such a way that there are 3 configurations. There is an item which is alone having value at least t, and there is also an item. Oops. Why? Sorry, can you hear me? Is it?
Yes.
Yeah, sorry. Yeah, because I have two pictures, and then on one picture there was something. Okay. Yeah. So right. So there are 3 such configurations. This is a 2-element configuration, and this is a 3-element configuration. You can imagine values which would give you that. Okay, and then this child would be happy with either one of these. And this configuration LP introduces one variable, enormous number of variables actually. For every player, it takes every configuration and introduces a variable, positive variable for it. And there will be a constraint for every player, namely that if you sum up these variables for all the configurations, you should get at least you should get at least 1. Every child should be satisfied, and for every resource, if you sum up all the configuration variables, you should not get more than 1, so you don't use any resource more than once. And you can think it through that if you would have a 0-1 solution to this LP, then you would get an integral allocation where the ones will tell you which configuration goes to which child. And well, one advantage, or yeah, so this is important to note that the VR seemingly are not present in this LP, but they are, because we are defining the set of configurations, hence the set of variables through these through the VRs. And the last comment I want to make with this configuration LP, that this previous one very valuable resource counter example can be detected because in this case, for any t which is positive, you have just the set of configuration is just this one element set for every player. So the first condition is telling you that every variable should be at least one. And the second condition tells you that the sum of the variables should be not more than one. So that cannot be if you have two players. So this problem with this somehow bad example disappears. Okay, good. So what we are interested in, you can already see it from my first remark, is whether for a given t, this thing is feasible. And in fact, we are interested in the largest possible t, such that this is still feasible. And that T star, this is what we will call the value of this, and this T star is an upper bound on the optimal value of our Santa Claus problem, because of the second comment, or the first comment, that an integer solution will be also a feasible solution here with that value. Now, right. So what we are interested in is to determine the integrality gap of this CLP, which this is what I call the integrality gap. This is right. So this is note that this is not right. So this is not one LP. You don't know this T in advance. What should you look for? But Bansal and Sviridenko showed that even though you have really exponentially many variables and it's a huge LP, and you have to find a T, you can approximate this T star up to any precision you want in polynomial time. Okay, so this is just something we accept. So it means that if you, for example, you determine this T star up to delta precision, then you will have an idea about and you know the integrality gap. That means that you have an idea about how large the optimum value is. Okay, so
and you can do this, Tibor, and you can do this because of this Gretchen-Schreiber theory and ellipsoids and so on.
Yeah, I don't remember. I think they do something with knapsack dynamic programming for the knapsack problem, but I don't exactly remember how they do it. They go to the dual and then somehow, right? Yeah, I'd rather not say. Yeah, so so it's. I mean, if you are coming from outside, this is surprising. Yeah. Now.
But not if you are coming from the North Pole. Right?
Yes, North Pole, right? Not then. Yeah. So let me, to get maybe a bit more familiar with this configuration, let me give you a proof. Of course, Bezakova and Dani showed that it's unlikely to have a better than 2 approximation, but now we give a proof that is independent of PNP, such that the integrality gap cannot be better than 2. And the example is very simple, and it is maybe instructive to go through it just quickly, that we have 4 children, and each of the child, you can see their liked set. They have 3 liked set. They have these weights, 1, 1, and then 4 items with 1/2. And you can take a look and see that A and B, only one of them can occupy this value 1. Also C and D, only one of them can occupy this 1. So you would have to give this 1/2 to the remaining 2, but these matchings are chosen in such a way that it's impossible. So you cannot give them all these items, and that means that the maximum mean allocation will be 1/2. On the other hand, the CLP with target 1 is feasible. So you simply give 1/2 weight to every single. What are the configurations? The configurations are the singletons and all the pairs which are coming from 1/2s, right? These, and these 4 pairs. And you give 1/2 to each of these variables. And then if you sum it up for each player, you see that you have exactly 1 weight summed up on its set. And if you sum up for each resource, what you get, each resource has degree 2 in this hypergraph. So they will also get value 1. So this is feasible. So there is a factor 2 difference. Okay. Now, obviously, after Bansal and Sviridenko introduced this configuration LP, there were great interest. First of all, they already used it to derive an approximation algorithm with factor which was depending on P. Earlier, there was nothing known. So it was depending on P, but very weakly. And the development, I wrote 2 columns. One is about the approximation algorithm factor, and the other is the integrality gap. And they went parallel. And the integrality gap always went a little ahead. So Freie gave an algorithm using local lemma many times, which gave a constant factor, which was an integrality gap. Yeah, so it was a huge constant, but it was at least a constant. And this was a time when local lemma got algorithmized, and this was turned into an approximation algorithm with constant, again, huge but constant factor. And on the integrality gap, very soon there was a huge breakthrough. The constant factor was reduced to 4. And this was using Haxell's combinatorial hypergraph matching theorem and the algorithm inside it. Well, the algorithm was not used, but just the idea. And the algorithm later was the algorithm in Haxell's paper is really non-polynomial, but people went into this proof and they really changed it, and then based on this, the factor went down slowly, first quasi-polynomial time, and then slowly went down to the current best, which is 4 plus delta, right? So these are all using configuration LP together with Haxell. And recently, the integrality gap also went below, again, overtook the algorithmic results, and now it stood at 3.808. And all these proofs and algorithms do build on this combinatorial technique. And what we do is we improve this integrality gap using a different technique, which is not that unexpected in this, once we are using the hypergraph matching theorems, but it's surprising how much better it does than the combinatorial ones. So we achieve this 3.534 integrality gap, and I would like to tell you a little bit about the proof in the remaining time. Maybe I first state our other result. So we have two results, one for the general problem, which is this 3.534. And there was a very interesting special case also studied, which is due to Chan, Tang, and Wu, where you have only two weights, and one big and one small. And they showed that the Bezakova and Dani MP hardness proof also is valid for this very special case. So you cannot expect better than two approximation. And they showed that the integrality gap, on the other hand, in this special case is at most 3. So what we can do with our method is to reduce the 3 significantly when we really have tiny big difference between the weights. So we have a somewhat so we have some function that the integrality gap is governed by this function. It's almost always better than 3. In a significant portion of the parameters, it's better than 2.75. This is somewhat arbitrary, but in the limit, when x goes to 0, this is 2.479. So this is the limit of at least our method at the moment in this example. So here you can see that this is we are identifying here 2 instances where this could still be 3, and this is really, I think, maybe one message of this theorem, that it identifies if we want to have an example which is better than the 2 approximation, this MP hardness, then maybe these are instances one could specifically look and search for examples. Okay, so are there any questions about the theorems? I would speak briefly about how we are dealing with it instead of the combinatorial. Okay.
Sorry, Tibor, which of the 2
yes.
proofs are you going to describe? The first or the second?
So both proofs are the same, not the same, but the same method. And you will see the method. I'm not gonna tell you the proof of the 3.534. I'm gonna tell you the proof of 4, right? Which was already known 10 years ago, but in this language. Maybe I give you an idea how you do 4, and then I give you an idea what it takes to improve it. And maybe also that why we improve it and why it is more difficult in the other with the other technique. So what we will do is we will formulate the problem into a problem of independent transversals in a certain auxiliary p-partite graph. So we decide on some approximation factor alpha we want. So our goal is to get an allocation whose mean value is alpha times t star, which is the value of the configuration algorithm. And in such a problem, we can take a look at the hyperedges. These, we call them alpha hyperedges, which are interesting for us. What are they? They are the ones which do have value alpha t. They are part of some light set, and they are minimal. I don't want to take more than I need to. And then I need to select one such alpha hyperedge to each player, right? So what I'm looking for is, here I'm going to have, here are the players, here is a sack, and here are two light sets of these two players, P and Q. And you can see in the red that these are the alpha hyperedges. These have value alpha t star, okay? And this is a multi-hypergraph. So for example, this edge here, this 2, is part of both LP and both LQ. Its value is at least alpha t star. So it is it has 2 copies in this multi-hypergraph. Okay, and now how can you do a graph from it? Well, here it is. For each player, you create a vertex set, and each vertex will be one of these alpha hyperedges, and you connect 2 alpha hyperedges if they intersect, right? Because that means they cannot be allocated, both of them, to their respective owners, because they intersect, and they share some resource which cannot be allocated to both P and Q. So this is this graph, and very important, inside here you don't draw any edges. I don't care that these alpha hyperedges here intersect. I am looking for an independent transversal, so I am not drawing these edges. I don't care if these alpha hyperedges intersect. And then if I find a independent transversal, so here you can see this independent transversal. This is a set of vertices, one in each class, such that they don't have any edge. So that means they correspond to 4 disjoint sets. Each are inside the light set of the respective players. So they form an allocation we want, and their value, the mean value, is enough. It's alpha t star. So what we just did, we reformulated the problem into finding an independent transversal in this auxiliary graph. And what we will show is that there is, if this parameter here is, this alpha is 15/53, then this graph has an independent transversal. Okay. Good. So how to find an independent transversal in a graph? This is a very, very well-studied problem, and actually, this is a problem which I usually, there is a classic one, which is this, what is the, if you have the maximum degree delta, what is the smallest size of the vertex sets, which guarantees that there is still an independent transversal, no matter what the graph is. And the exact value is 2 delta. So for any maximum degree graph, maximum degree delta graph, there is an independent transversal if the part sizes are 2 delta. Okay, and this is tight, and there is a construction that has 2 delta minus 1 part sizes, and there is no independent transversal. Now, this is interesting because this is a problem which is a really nice example where you could use probabilistic, you could use combinatorial, you could use topological tools to attack it quite effectively. So for example, with the local lemma, you get something which is maybe 2e or 4e, I don't remember. So something not 2 delta, but maybe 4e delta or something sizes, so it's a bit weaker. And then combinatorial, you can get to 2 delta, and you can also prove that topologically with the methods which we will study here. And you could imagine the same development happening in this problem as well, because what the first constant approximation for this problem was given by local M, also the algorithm, and then you got a lot of ideas and developments using the combinatorial tools, which essentially also give you independent transversals. And what we do is we essentially do the topological tools and apply it to this problem. And here, on the other hand, it gives something better. So how to find an independent transversal? So I have 2 minutes, I guess. There are 2 theorems which are crucial for us. One is the following. So for a graph, we will consider its independence complex. And there is this parameter eta, which is essentially the topological connectedness of this independence complex plus 2. Okay, this plus 2 is this just shifting, and it has a much nicer properties than the usual connectedness. So you could read the properties here. And this, given a partite graph, an ipartite graph with vertex set like this gives you a whole type condition. This is a theorem of Meshulam and Aharoni-Haxell implicitly also, that for every u, you have that this connectedness parameter of the graph G, if you restrict it to the classes by the indices in U, this is at least U. So this is really like a whole type condition. Then G has an independent transversal. And this is going to be our tool to show that there is an independent transversal. We will apply this to this graph, which I described above. And the question is, of course, how do you prove that this eta of some graph, right? We have to look at many graphs because we have to restrict to some U. How do you prove that this is large? And here we are using a theorem of Meshulam, which is in a way gives us a tool to dismantle, to define a process to dismantle a graph. So what does it say? It says that for any graph and any edge in this graph, the eta of G is lower bounded by 2 smaller graphs, eta, the eta of G deleted with this edge deleted, and 1 plus the eta of G, this edge exploded. What is exploded? Exploded is that you remove the edge and you remove all the vertices in the neighborhood of the edge. And this theorem is giving us the tool to define a process, which was used also in various other scenarios by Aharoni and in many papers, where you define a process where you take a graph and you delete an edge. If it's deletable, what does it mean? That its eta does not grow. And you explode an edge if it's explodable, if this is the minimum, right? So if the exploded is not more than eta of G minus 1. Now, in such a sequence, you just do this starting from your original graph. And then you go. You always in every step delete or explode. One of them is possible. And at some points, you will have a graph with no edges. Okay, and then there are 2 cases. Either this graph has an isolated vertex either this graph has an isolated vertex, in which case you are done, because if you have an isolated vertex, then your connectedness is infinite, or this graph has no isolated vertex, it's empty, but then you can count how many explosions did you do in the meantime, and the connectedness will be to lower bounded by the number of explosions. So our goal is to define a deletion explosion sequence, a D sequence, that ends up long. Either it is a sequence which ends up with a graph with an isolated vertex, or it has many explosions. And that's how we show that the eta. Unfortunately, I do not have time to show you more. So in order to make this happening, we are using the dual of the configuration. At some point, it has to come in somewhere, and we are using the dual to make sure that this process of cleverly defined deletion explosion sequences go a long way and include many explosions. Okay, so I will stop here. Maybe I will say just the two obvious open questions, which are somewhere here. Our results are purely on the integrality gap. We don't know how to algorithmize it. We give the existence of such allocations. We don't know how to get them. And it will be already interesting to have quasi-polynomial algorithms here, which are better. And in particular, from our second theorem, we will be really interested in finding a 1/1/3 instance, if it exists, which has a T star, which is 1, but has no allocation with max min 2/3. That would mean that we improve that impossibility of integrality gap up to 3 and not just 2. Okay, so thank you very much. I stop.
Thank you. Any questions? So the reason why you don't have an algorithm is because you use topological method, right?
Yes and no, right? So at the beginning, you also did not have algorithm when you use the Haxell augmenting tree algorithm. That's an exponential algorithm. So the fact that at the moment we don't have an algorithm does not mean that one cannot look at this proof and cannot find a way to somehow make it work in the future. So, right. Yeah.
Any other questions? If not, let's thank the speaker again.
Thank you. Thank you, Hong.